Hello, welcome. In this short video, let us look at the non-linear nature of a biased averager. So let us consider the following system equation: y of t given by b plus 1 by t integral t minus capital T to small t x of tau d tau. So it's like this function or the system is like a running averager, but with an extra bias b added to the output of this integration. So here we are going to verify that this system is actually non-linear, or we are going to prove that the system is non-linear. So to start with, we have to think about the linearity property. That is, for example, when you send a signal x of t through a linear system, so for a system that gives the output y of t, and if the system is linear, then an input alpha of x of t should also give the output alpha times y of t. So that is a linear system. So if the input is basically scaled or multiplied by a parameter alpha into x of t, then the output should also be multiplied by the same parameter alpha. So let us verify if this property is satisfied by this system function. So when alpha into x of t is the input, then let us say y dash is the corresponding output, and it is given by value b plus, then we have 1 by t integral t minus capital T to t, so this is small t, and then we have alpha times x of tau d tau. In other words, when we replace input x of t with alpha times x of t, what we get is y dash of t, that is the corresponding output is y dash of t is equal to b plus alpha times that average. And now consider the output that we assume or we expect in a linear system. That is, the output that is expected for a linear system is alpha times y of t, which is given by alpha times b plus 1 by t integration t minus capital T to small t x of tau d tau. So this one is alpha times b plus the average. So clearly alpha times y of t, which is the expected output, is not equal. It is not equal to y dash of t, because that y dash of t has only a b, not alpha b. So the system is non-linear, and clearly the system becomes linear. That is, the system will be linear if that bias b is exactly equal to 0. So that is the condition for making the system linear. Now let us look at the Matlab implementation of this idea for a simple example. That is, we assume that the input x of t is like an exponential of minus 2t. In that case, we can calculate the theoretical value of the output, that is when it is alpha into y of t, and we can also calculate y dash of t, that is, it is b plus alpha into the average of the signal. So we compute those two values. So basically we assume the value of t, that is the averaging time, and then we create the sampling rate, and then the value of m, which is basically giving us the length of the total time, and that is basically the time vector, and then we have the parameter alpha, and then we also have the bias b, assume it to be 2, and based on then once we have all the constants and the time vector, we can create the signal, generate the signal x of t, which is assumed to be exponential of minus 2t, and then we compute the theoretical value of the output y of t, that is alpha times y of t, and then we compute y dash of t, which is b times alpha into the average of the signal of length for a time capital T. So we then we can compare the results, that is, we compare the two results. So the red one basically shows the output alpha into y of t, that is the output if the system was a linear system, and then this blue circles basically is the actual output, that is when we get alpha into x of t as the input, then the corresponding output will be actually y dash of t. So clearly the red one, the red curve and the blue curve are not the same, they do not agree with each other, so the system is not a linear system. So since y of dash, or in this case y1 of t, is not equal to alpha into y of t, that basically means that the system is non-linear. So when we make this b, that is the bias, equal to 0, we can clearly see that both alpha into y of t and y dash of t are exactly equal. That means it becomes a linear system. But when b is not equal to 0, say any other value like say 2 or 3 or whatever it is, non-zero value, then clearly there is a disagreement between the theoretical, there is a disagreement between alpha times y of t and y dash of t. That means the system becomes non-linear. So to summarize, in this video we have looked at the non-linear nature of a biased averager. Given the system function y of t equal to b plus the average of the signal over a length of time t, so we want to basically show that this one is non-linear. So first we have to look at the linearity property. One part of this is when we give alpha into x of t, that is a weighted input, we should get exactly alpha into y of t as output. So when we give alpha into x of t as the input, the actual output we get is b plus the average, and alpha times y of t is alpha into b plus the average. So obviously these two are not same, so it is a non-linear system. And then we have verified the same thing in Matlab, that is when b is not equal to 0, that it is a non-zero value. We found that alpha into y of t is not agreeing with alpha, y dash of t, and when b is exactly equal to 0, that is when b becomes vanishes, that is when b vanishes, we can clearly see that the output alpha into y of t is exactly same as the actual output y dash of t. That means the system becomes a linear system. Thus we have verified that the biased averager is a nonlinear system. Thus we have verified that a biased averager is a nonlinear system using both the theory and Matlab. And when the bias itself b becomes 0, the system becomes a linear system. Thanks for watching.